Okay, so he took a, so let me start again. So for the first question, what he did was he created his own hash function that takes any arbitrary length, does the hash and gives you a 256 byte result. All right, and to test it, what he did is he took a message M of 4096 bytes. All right, and he did the same hash function, correct? And then he produced the 256 byte hash. Okay, and what his friend Eve did is she said that she was able to find another message M, okay, that was where you did the hash function, and it produced, okay, it produced the same digest. That means it produced the same 256 byte hash, okay, with a different message. Okay, so that is the information that we have. All right, now what properties are lacking from this current hash function that has been developed? Okay, so let's look at it one by one. Okay, for the first one, non-trivial. Okay, non-trivial means it must not be something that is too simple or too straightforward. Okay, so that is what I mean by non-trivial. And when you look at this, it seems like two messages which are different can end up having the same hash function, correct? So what is lacking? Okay, so you can maybe this could be the answer, maybe it's not, but let's look at the others as well, correct? Sensitive to input change. Okay, so for this, for us to know whether this could be a factor, we should actually sort of know what is M and what is M prime. Okay, but we do not know, right? We just know that it is different. Okay, so since we do not know how much this difference is, we can't really say that this is an issue. Correct. So we can't pinpoint to point 2 to say that this could be an issue. Point 3 is definitely not there as well, because there was no talk about going back to M, correct? We never said that hash we can decode back to M. So the only thing that we know for sure is that the converting the message to the equivalent hash function itself is currently non-trivial. Okay, because 2 and 3 we cannot deduce from this information. So the only thing we can conclude is it is non-trivial. Okay, so that is the answer over here. Okay, so that is why it's only 1. Okay, because for 2 and 3, 2 we don't have enough information to say that it could be 0.2, and there is also no information of whether we can go back to the message. All right, from the hash function. So 2 and 3 we cannot say from the information given. So only 0.1 is what we can conclude from the current hash function that we have. Okay, so that is how we are able to narrow down and say that it is 0.1 over here. Okay, let's go on to question 2. Okay, so I will just go through and discuss. If you have any doubts, you can ask me. Okay, if not, I'll just proceed. Okay, for question 2, okay, the TLS certificate of a website, okay, is publicly available. Okay, that means everybody can access to it. Okay, so all you need to do is to send a request, and then you can receive a copy of the certificate from the website. Okay, so the certificate is publicly available. And what we have next is Alice thought that she can make the website more secure by encrypting the certificate using the requester's public key before sending it out. Okay, so, and the objective of that was to prevent any third party to get a copy of the website certificate. Right, and for this question, you can see that firstly, if the certificate is publicly available, that means anybody can request, anybody can get. Correct. So the person who is the requester could also be the attacker. Correct, because if I want to attack, I can also pretend to just be a normal person, and request for the certificate. So even if you encrypt it, I will still be able to decrypt it in my own private key later on. Correct? So this idea that Alice has is not going to work, okay, because the attacker can also be anybody who is just going to request the certificate. Okay, because effectively Alice is just going to encrypt it using the requester's public key. So since the attacker can also be the requester, this idea that this is going to actually help in any way is wrong. Okay, it's not going to help in any way. All right, so that is why the answer for 2 is E. Alice is wrong because the attacker can also be the one who is requesting the certificate. Okay, for question 3, okay, we are using, okay, the question is asking us, we are using bare metal programming to send out an array of 64 integers, okay, from the at mega 328, which is our UDRO. How many times do we assign or place a value in the UDR0 register for transmitting the entire array, okay, using polling or interrupt? All right, so if you remember your UART protocol is basically for transmit, okay, for transmitting, all we need to do is we write the information to the UDR register. Right, so if this is my UDR register, I write the information there, and then it will start to transmit out. Correct. The only difference between polling and interrupt is, for polling, I need to keep on checking for the status bit to be set. Then I know that the transmit has completed. Then I go on to the next byte. For interrupt, after the transmission is done, the interrupt is generated, and then I will be able to proceed with the next byte or next information that I want to transmit out. Okay, so in terms of polling and interrupt, you will actually be writing the same number of times to the UDR register, correct? Because the amount of data that I want to transmit out is the same in both cases. So I will still need to write that same number of times to the UDR register. Okay, so the only two possible options are A and B, okay, because it has to be the same number of times. Now the only thing is we must remember that from our studio, that for our Arduino Uno or 8328P, okay, when we say int integer, it is actually 16 bits. Okay, so in order to send out 16 bits, I need to break it up into two separate writes to the UDR register. So that is why for the 64 integers, it is equivalent to 128 bytes that I need to transmit out. So that is why the answer here is B. Okay, so that is again something that we sort of got exposed to when we were doing that studio on serialization and communication. Okay, so if you remember the studio where we looked at this data length difference, the padding of the character and so on, so that is where we discuss all of this. Okay, so that is our question 3. For question 4, okay, so what we have is, suppose each of the RPLidar scan data takes 4 bytes. What is the minimum bandwidth for the serial communication between the RPLidar and the Pi if the LiDAR is operating at the optimum 10 Hertz scanning speed? All right, so the way you go about doing it is, we know that one scan, so if I say this is my starting point, one scan is 360 degrees, all right, 360 degrees of points that I need to scan each time I go for one revolution. Okay, and I'm going for how many times in 1 second? It is 10 Hertz, correct? So I need to do 10 rounds in 1 second, correct? 10 rounds in 1 second. And each time I scan, each scan data or each point is 4 bytes. Right, so I need to multiply by 4 bytes. Okay, but the communication is in BPS, correct, which is bits per second. All right, so for bits per second, I need to multiply by 8 to know the actual number of bits. Okay, so if I multiply all of this together, I would be able to get the answer here, which is 115200 bits per second. Okay, so that is how you get the answer here. Okay, so let me go on to the next question, question 5. So which of the following regarding the Hector SLAM used in our project is correct? All right. Okay, let's look at point 1. Point 1 says it estimates the movement using compass and magnetometer. So this is definitely not true because we did not even use these components. So it's not true. Hector SLAM does not use odometry data from the motor. So this is true, correct? Because if you remember Hector SLAM, what it does is it tries to estimate your new sort of mapping based on the information that is already observed. Okay, so it does not require any odometry data. Okay, based on the map that is always changing and is observing, it tries to map out the environment using that alone without the odometry data. Okay, point 3, Hector SLAM differs from other SLAM algorithms as it does not try to re-observe landmarks. So this is also false. Okay, it does try to re-observe landmarks. Okay, so as it is moving, okay, based on the landmarks it has observed, it will continuously observe the same landmarks as well as new landmarks, okay, for it to come up with a map of the environment. Okay, so the only thing that is true here is point 2, okay, which is that it does not use odometry data from the motor. Okay, so that is what we have for question 5. Okay, so let's go on to question 6. Okay, so the next few questions on the ADC part. Okay, question 6 is basically I think if you look at our ADC slides, I think one of the first few slides already you will get the answer. I think the tricky part here is, of course, you must know that it is mentioned that this is the board that you're using in your EVP2 lab. Okay, and why is this information important? Because the AT328P has a few variants. Okay, in terms of the packaging, the one that we use in our lab is the DIP package. So in that particular package, you have slightly lesser pins, so you only have 6 ADC input channels. Whereas there is another packaging which I had shown in our ADC that lecture slides, all right, or the tutorial slides, one of them. That package, which we call the quad flat package, okay, or TQFP or QFP, that one has more pins available, and in that you have 8 ADC channels. Right, but the one in our lab, that packaging, the DIP package, actually has only 6 ADC input channels. All right, and of course, regardless of the package, we only have 1 ADC module. Okay, so in terms of ADC module, we only have 1, but the particular version that we use in our lab has 6 ADC input channels. So the answer here is C. Okay, so that is question 6. Question 7, an input signal is in the range of 0 to 0.6 volts. Okay, and what is the largest ADC value you can expect? Okay, so basically our Arduino Uno, okay, the ADC module can have values from 0 to 5 volts, correct? Okay, and since I only have a range of 0 to 0.6, the maximum value is 0.6, okay, out of the full range of 5, multiplied by 1024, which will give me 122.88, okay, which is rounded up. So the question itself say we will round up the ADC value. So the largest value is 123. Okay, so that is how you get the answer D over here. Okay, based on the input signal of 0.0 to 0.6 volts. Okay, so see, for question 8, what is the gain necessary in order for the input signal to be mapped to the full input range of the ADC module? Okay, so what we are saying is we have a signal that is very small, okay, 0 to 0.6, and we want to map it to a range of 0 to 5 volts, correct? So the gain that we require is 5 divided by 0.6, which is 8.33. Okay, so that is what you have. So the answer here is A, 8.33. The next question, okay, what is given is the correct gain is provided. So of course, you need to make sure that this answer is also correct in this case. So the correct gain is provided and the ADC operation is performed. The ADC result is this. Okay, so this is a 10-bit binary value. What is the actual voltage of the signal corrected to decimal places? So this is what you get at the ADC part, correct? So this is the ADC module, and out of this you get this this binary value, and this binary value is equivalent to 250. Okay, so you get in your calculator, then you'll get that it's converts to 250 decimal. Now this 250 decimal, with reference to the range of input signals 0 to 5 volts, what does that represent, correct? So is 250 divided by 1024 times 5, right? Because the 10-bit ADC and the input range of the ADC module is 0 to 5 volts. So what you get is 1.22 volts. Now there's still one more step, because this is the signal after the gain is provided, but the question is asking the actual voltage of the signal. Correct. So I actually had a gain over here. Okay, and that gain was this value of 8.33. So I had a gain of 8.33, and this is the original signal. This is the actual signal. All right, so what I need to do is to get the actual signal, I still need to take 1.22, go back, okay, so divided by 8.33, and that will give me 0.15 volts, which is this. All right, so that is how you get the answer 9 for part D for question 9. Okay, for the next question, question 10, you decide to operate timer 0 in fast PWM mode. Okay, so in fast PWM mode, basically it goes from 0 to 255 and then comes back down again. Okay, so the frequency of the PWM is given as the clock frequency divided by 256, which is 16 megahertz divided by 256, which is 62.5 kilohertz. Okay, which is your answer here. Okay, now let's okay, so the question is, this was tested in quiz 1, will it be tested again in quiz 2? Okay, so for my part, this will not be tested, okay, because we already covered this in our quiz 1. Okay, so for our quiz 2, I will not ask you any questions regarding the PWM operation. Okay. Okay, for question 11, it is about the TLS operation. All right. Again, this this answer may not necessarily apply to us right now because things were a bit different then. Okay. So over at that time, we did not do the client side checking. Okay, we don't do the client side checking. Okay, we only did the server side checking. All right. So the reason why, so for this, the answer that is given here is C. Okay, and why is it C is because when the client verifies the only the client side, okay, we did not do the checking. Okay, only the server side checking was done. All right, which means that any client could connect to the robot, okay, and then control it. All right. The other options are not true. Okay, why? Because the encryption that we use is, of course, the TLS algorithm. Okay, and this TLS algorithm is actually an industry standard algorithm. Okay, if it was weak, nobody would be using it. Okay. Again, the key exchange mechanism that we used again is the Diffie-Hellman key exchange, which is also industry standard, correct? So it was what we did in our studios was actual industry standard approaches to doing the key exchange and the encryption and all. So there was definitely no issue with that. So definitely this is not true and this is not true. Okay. And using 2048 bits key is too small is also not true, because that is also a standard. The RSA key length is also a standard practice. So this is also not true. Okay, and of course, D and E are sort of linked together because they are both talking about the encryption, which is using the RSA standard. Okay, so the rest of them are not true in this context. So the only thing that was not done at that time was we did not specifically do the client side check during that particular year's studio. So that was the weakness at that time. All right, so that is why for this question it is C. Okay, based on what was given to the students at that time. Okay, so let's go on to question 12. Okay, so question 12 is about the deserializing and serializing. All right, so what we have is we have a data structure here. Okay, and from this data structure we create a data variable. All right, and then we copy this information to the buffer. All right, and then we send out. Okay, so it is given that it is a highly reliable channel without any loss, okay, or corruption. When Bob gets the message, he decrypts it or deserializes it. Okay, okay, it seems like some things got cut off here. Okay, maybe I copy that information. Give me a minute. Let me copy that. I think something when got cut off when I copied that data over. Okay. Okay, so this is the part on the Bob side. Okay, when he gets a message, he deserializes it. Okay, using this approach here. And what is given is the data he gets is garbled. Okay, that means it gets messed up. Okay, which of the following is not a possible cause for the data being garbled? All right. So what could be not a possible cause? Now let's look at these one by one. The first one, the integer and or floating point widths used in Alice and Bob machine are different. So this is true. Okay, this could be a reason, correct? Okay, because we have seen this in our studio itself, where the RPi and Arduino are communicating, and if there's a difference in the widths used, it's an issue. The byte ordering is also an issue, okay, because as we have seen, we have a Little Indian and Big Indian system. So if the byte ordering is not aligned, then that is also an issue. Now let's look at C. Bob uses a buffer, okay, that is too small. Okay, so that buffer referring to this here. So over Alice, he uses a buffer of 255. Here he uses a buffer of 128. Now, is that an issue here? So to know if this is an issue, we need to look at how big is this actual data going to be, because we only copy one instance of this data to the buffer. And if you look at this, okay, even if you take it as maybe we do not know the system, correct? Okay, but let's just assume that maybe this is 4 bytes and this is maybe 8 bytes, okay, and this is 6. Okay, so this is at max probably 18 bytes of information, correct? Okay, so even though we do not know, if we just try to assume some high number, one data structure variable at most is probably going to take about 18 bytes of space. Okay, so whether I declare the buffer as 255 or declare the buffer as 128 will not be an issue, because it is big enough to hold the information that is being sent over. Alright, so this is definitely not a issue. Alright, the compiler used in Alice and Bob machine are padding in different number of bytes, so this could be an issue, correct? Because we do not know the information, we do not know what compilers they are using, how they are behaving. So it could be that padding is done differently, okay, different number of bytes and so on. Okay, and all of the options are possible causes. So this is also not true, because we know that C is so we know that C is not a possible cause for the data becoming garbled. Okay, so the answer for this is actually C. Okay, that the difference in the buffer size is actually not an issue, okay, in this situation here, for the data being messed up, okay, when Bob receives it. Okay, so that is why we say the answer is C. For question 13, which of the following statements about serial communications is false? Parity checks cannot detect an even number of bit errors in a byte. This is true. Okay, we have I've discussed this in our class, both in the studio and the tutorial, correct? When there's a 1 bit change, you can detect it, but the moment there's another bit change, okay, it's sort of it's like two negative cancel out each other. All right, so you will not be able to detect it just by using parity checks alone. Okay, so this is true. The receiver and transmitter must have the same baud rate and frame format before they can communicate. This is of course definitely true. The transmitter must send clocking information to the receiver before transmission begins. So this is false, okay, because both the transmitter and receiver must already be pre-configured, okay, to operate at a particular clocking rate. All right, so if the transmitter is at 9600, the receiver must also be at 9600, okay, and then from there you are able to communicate with each other. So the clocking rate should have already been set to match. Okay, both of them must already been set to match before you can start the transmission. Okay, so there's a question here saying, is there a specific type of frame format for error correction? Okay, so there is no error correction here. The only thing we can do is error detection. Okay, the current UART protocol, by just sending the data, we just having odd or even parity, we can detect error, but we cannot correct the error with that data alone. If you want to correct error, you can't actually do it. The only thing you can have a sort of communication protocol where you say that if I detect an error, I send back another request to resend the data or something like that. Okay, so when I receive the packet and if there's an odd number of errors, yes, I can detect the error, but after that, I will not be able to do anything else about it. I can, if I have a communication protocol in place, okay, so for example, if I have the TX and RX, okay, so if I receive and I say that this is an error, then probably I can just say, can you do a resend of the last data and then try to send back and see whether it's okay. So that is what you can do at the protocol side, okay, but the UART itself cannot correct any error. Okay, let me see, there's another question. Okay, Okay, for D, the serial line is normally held in logical high, but is pulled low just prior to sending the first bit. Okay, so this is true because if you remember our protocol, the idle line is high, okay, and the start bit will actually pull it low. So the first bit is actually the start bit. Okay, and then you start to have the transmission, everything. And after everything finished, then you have a stop bit. And after the stop bit, okay, that is the one full packet that you transmit over the channel. Okay. The last line, in N-mega-32A, sending in double speed mode can result in more data being incorrectly received due to poor build or poorly built system clocks. Okay, this is true. Okay, in a sense that when you have higher bit rate, it means that you need to be able to have systems that can reliably transmit and receive at that same rate. Okay, and again, this may not always work for some simple systems where the clocking may not be as efficient or as accurate. Okay, so that is why even our RPi to Arduino, okay, generally we do not clock it at a very high rate, even though if you look at our UART channel, we can actually configure them to go at very high bit rates, but we actually go down to I think only 9600, okay, for our lab. Okay, because that bit rate is good enough and is more reliable. Okay, so that is why we do not want to clock it at too high a speed. So when you go very fast, okay, though the data gets transmitted faster, the chances of error are also higher. All right, so based on all this, the option C is the statement that is false. Okay, for question 14, given a transmission rate of 9600 baud in 8N1 format, what is the fastest rate at which you can write to UDR0 without causing any loss of data? All right, so 8N1 means basically you have 8 bit of data followed by one stop bit. Okay, so you also have to remember that you always have a start bit as well. All right, so one complete data packet that you want to send actually takes up 10 bits. All right. All right. So since I am operating at 9600, okay, bits, okay, per second. If I divide it by 10, that gives me 960. Okay. You can think of it as 960 characters per second. Okay, so when I say character means you think of this as one complete character where you have a start, the 8-bit data plus the stop. Okay, so 960 characters or 960 packets or how you want to call it, okay, is what you can send over in 1 second. So which means that the fastest I can update my UDR register is 1 by 960, which is 1.04 millisecond. Okay, of course, in practical sense, we do not update UDR based on this timing, correct? We update based on the actual interrupt or the actual bit that we pull. All right, but this sort of gives you an idea on actually how frequently that transmission will be completed if I were to operate at this particular baud rate and with this format. Okay, so that is this question 14 here. Okay, so the last question for this paper here was, which of the following statements about TCP/IP is false? Okay, so the first one, IP packets sent in sequence can arrive out of sequence at destination. This is true, correct? Because if you look back at your TCP/IP, the handouts, okay, the slides, you see that the packets can be routed through multiple sort of routers, okay, and eventually it will reach the destination. And it doesn't matter if it reaches it out of sequence, because there is a at the receiving end, you will be able to rearrange it in the correct order. So that is definitely true. IP packets that are sent out may never arrive at the destination, which is also true. Okay, because it is a best effort protocol. So when you send out, there is also a timing factor associated with it. If by a certain time it cannot deliver the packet, it may just drop the packet. Okay, so there's a chance that a packet that is sent out may never arrive at the destination. Okay, two IP packets bound for the same destination may travel over two completely different routes, which is true because it's similar to our point A over here. Okay, so they can be at very, very different routes. Okay, for D, if we receive a request timeout when we ping a host, it means that the host is down. Okay, for part D, if we receive request timeout when we ping a host, it means that the host is down. All right, so this ping, okay, when we try to ping a host, okay, we actually, what we are doing is we are sending over what we call a ICMP packet. Okay, so this was also covered at that time. I'm not sure whether this current set of slides we covered this or maybe it was taken out. Okay, but the ICMP packet basically means it's an internet control message protocol where we are able to get some information about the host or the server. And it's possible that the server may be configured to not actually handle this kind of request. Okay. Please don't handle it. Just give me a minute, huh? Okay, sorry about that. Okay, so for the last one, the ICMP, as I'm mentioning, there is a possibility that the server, okay, may be able to actually configure itself not to entertain such requests or to drop such requests. All right. So when we receive such a request, it does not mean that the host is down. It could be that it is just not accepting such a request. Okay, so this is actually false. Okay. The last one again is related back to the first part A. TCP ensures the socket application receives packets in the correct order. Okay. Okay, so this is of course like what I mentioned is the TCP protocol ensures that when I get all my packets, I will be able to rearrange them, okay, in the correct order, okay, because we know that they're going to arrive out of sequence, okay, but I'll be able to rearrange them in the correct order. So the TCP is in charge of ensuring that order is there. All right, so the one statement that is false here is actually the part D over here. Okay, there may be some things that maybe we did not cover as much here as we did in the past and so on. Okay, so sometimes some of the questions or some of the information that you may see may not necessarily be the same coverage as we had in the past, okay, as compared to now. Okay, now let me go on to the additional practice questions. Okay, so for these additional practice questions which were uploaded yesterday, hope you had a chance to look at them. Okay, the first question is about the sleep mode. All right. For this, what we have is our function where we are going to put Arduino to sleep. And what you see here is we have this first line of code here. And what does this line of code do is it activates the sleep enable. So when I set SE equals to 1, which is given in the question itself, you enable the MCU to go to sleep. Okay. And then I call the sleep CPU function. Okay, wait. So there's a request to repeat the previous question. Okay, let me go back there again. Okay, so maybe I go back again. All right. So the main reason is the host, okay, or the server could be configured to not entertain or to drop this kind of requests. When you send an ICMP request, the host can be configured to not entertain it or to drop it. Okay, so you may send a request and you do not get a reply. Okay, so that does not mean that the host is down in any way. It just means that it's not going to entertain your request. Okay, so the host is still functional, but it's just not entertaining the request. That is why the part D here is false. Okay, so that is the explanation for question 15. Okay, can. Okay, so let's come back to this question here. So in this question, when we enable the sleep mode, okay, what happens here is we call the sleep CPU function. Okay, so once I call a sleep CPU function, what will happen is you will basically go into sleep mode. Okay, and if you look back at the data sheet of your microcontroller, you will go into a sleep mode in idle state over here, because the rest of the bits over here, okay, 0. So in this situation, okay, when you're sleeping, you can wake up based on a certain number of ways. Okay, so all that is inside the microcontroller data sheet. Okay, I won't go through all of that, but you will basically be able to go into sleep mode and then come out of sleep based on certain actions that are performed. Now what is going to happen here is the moment I come out of sleep, what will happen? Okay, the moment I come out of sleep, I execute this line, correct? Because this function here puts me into sleep. Okay, and the moment I come out of sleep, I will disable the sleep mode. All right, and the reason why we want to do this is to make sure that I am going to put the Arduino to sleep only when I explicitly call this function and not accidentally by any other means. Okay, so it is intentional that I I enable the sleep just before I sort of enable the sleep mode functionality just before I call the sleep CPU. Okay, and the moment I come out of the sleep mode, I will immediately disable it again. All right, so the intention of this sort of 3 lines of code is to make sure that I enable it first before I call the sleep CPU function, and after that I quickly or immediately disable it. So it is not that I accidentally somewhere else I call a sleep CPU function. All right. So again, this is because you do not want this sleep CPU function to be accidentally called somewhere else and then you go to sleep where you did not intend for it. Correct. So that is why just before I call a function, I enable it, and the moment I come out of the sleep, I quickly disable it. Okay, so that is the objective of the code that you see here. Okay, for question 2, it's a bit similar to the tutorial questions. Okay. So what you're given here is you're given a voltage divider, okay, and connected to the Vref of a voltage comparator. And what you are given here is that the input resistance can go in the range of 5 meg to 10 meg. Okay, and you are already given this information. The R1 is 200K and R2 is 300K. So what is the minimum possible Vref of your circuit? Okay, so let's look back at the circuit here. So what we have here is we have 5 volts here. We have R1 and we have R2. So effectively at this point junction we have another R in. Yeah. All right. And what I want is, okay, so the Vref is calculated at this point here. Vref. Okay, so that means it is the voltage across the parallel combination of these two resistors, which will then be considered to be in series with the R1. Correct? Okay, so effectively this is a voltage divider. Right? Vref is basically this voltage, that means the combined voltage of these two resistors against the total resistance multiplied by 5 volts. Correct? So if I were to simplify it, it will look like this. Correct? It will be 5 volts here, R1 here, and another R parallel here. Okay, so that is basically how I can simplify the circuit. And what I want is, I want the minimum possible Vref, correct? If I want the smallest Vref, means the R parallel must also be the smallest possible value, correct? If I want the smallest Vref, this resistance, the R parallel, must also be the smallest possible resistance, because this is basically a voltage divider rule. Alright, the larger the resistance here, the larger the Vref. The smaller the resistance, the smaller the Vref. Alright, so if I want Vref to be as small as possible, R parallel must be as small as possible, which means that R in must also be as small as possible. Okay, so the R in that I must choose in this case should be the 5 mega ohm. Correct? So the R parallel in this case would be equals to 300K parallel with 5 mega ohm. Okay, so if you remember, for two parallel resistors, R2 times R in divided by R2 plus R in. Okay, that is your parallel formula, and that would give you a resistance of 283K. Correct? Okay, so the maths I'll leave it to you to do. So once I get that, that means in this circuit, my R1 here is 200K and my R parallel is 283K. So the Vref, okay, would be 283K over 283K plus 200K multiplied by 5 volts, which will give me 2.93 volts. Okay, so that is what you must remember. Okay, so if I want the Vref here to be as small as possible, then this combined resistance must also be as small as possible. If I want Vref to be as high as possible, then this combined resistance must be as high as possible. Okay, so that is the idea behind this question. Okay, so let me go on to the next question here. Okay, so this question is basically looking back at the ransacked algorithm. Okay, discussed in the tutorial. So all these steps here are basically the same that we had in our tutorial class. Okay, so question 3 here asking us, suppose a malfunctioning LiDAR sensor return one round of scan data that are more or less random. Okay, so what we have is, we have a malfunctioning LiDAR, that means something has gone wrong. Which of the following parameters helps to ensure that the ransack algorithm terminates instead of going into a infinite loop. Okay, now when you say infinite loop, okay, that means you do not want it to keep on scanning and scanning indefinitely, correct? All right, so if you remember the ransack algorithm, what does it do? It looks, okay, so this is a while loop, correct? So while they are unassociated lidar readings means there are still readings which they cannot map back to any particular landmark or obstacle or anything like that. Okay, and the number of readings is larger than the consensus. Consensus means is the number that you need, okay, in order for you to come up with a proper mapping of of some boundary within the map. Okay, and we have done less than n trials. Okay, now if my uh, lidar is malfunctioning, which means what? Which means that I will not be able to come up with any form of consensus, correct? Okay, because uh, definitely the number of readings, okay, will always not fall within the number that I need to come up with a proper boundary or proper obstacle definition, okay, within the map. Okay, so C is not going to be a factor in making the thing stop, correct? The number of sampling points near a selected point is also not going to make any significant impact because currently the lidar is not functioning properly. So even if I have more samples or less samples, I cannot trust the sample data in any way, correct? So it will still be some data, okay? And I cannot really say whether this is true or false data because the lidar itself is not functioning correctly. So the only thing that's going to help me to stop the algorithm after a certain period of time is actually the n, which is the number of trials. All right, so that's why the answer for this is actually n, because that is basically the limit by which I will stop the scan. Okay, so regardless of whether the lidar is functioning or not functioning, how many samples I take, how many consensus points I have, it doesn't matter. Eventually, once the n runs out, I will actually have to stop. Okay, so that is why for this question, the number of trials will be the parameter that helps to ensure that I will eventually stop the scan. Okay, even though the lidar has malfunctioned. Okay, now for the last question here, which of the following statements is true, okay, regarding the parameters used in the ransack algorithm? Okay, a small consensus value increases the number of false positives that are in the real world. Okay, all right, so if you imagine, okay, so when I do a scan, okay, so for example, I do a scan and I have a small angle here. Okay, I call this the degree. Okay, so within a small angle, I try to get some points and I try to see if these points, okay, that I get, so some of the points can be further away, some will be closer. All right, if I say a small consensus increases the number of false positive, what does that mean? That means I am willing to take, like, for example, even if just 1 or 2 points are along this particular line, I say this is actually a line map. Okay, so that could be a false positive, correct? Rightfully, I want more points that are closer to a particular scan for me to say that yes, there is a proper landmark here, correct? A proper wall here. Right? If I decrease that consensus value and say that just a few points is enough for me to confirm a wall or a landmark, then there's a high chance that this could be false positives. Okay, so definitely this is true. Okay, x is the distance from the best fit line used to compensate for the x. Okay, so line 2 says X, which is the distance from the best fit line, can be used to compensate for the accuracy of the LiDAR unit. All right. So this X is the distance over here. So for each of the point, there is a distance from the point to the best fit line. Okay. Now, if this distance can be used as a way to compensate for the accuracy, all right, because we know that the LiDAR is not very accurate, so there will be some error. Okay, so can we use this distance to have some compensation for the accuracy? Okay, so even though the current distance may be maybe 0.4 cm or something like that, but we can say we can compensate and say that there's an accuracy of 10%. So I compensate and say I accept anything within plus minus 10%, and that can actually help to add on to my number of points for the consensus. All right. So this distance that I get can actually be used to compensate for the accuracy in the LiDAR unit. Correct. So that is definitely true. And the parameter D controls the likelihood that the points selected for the best fit line come from the same landmark. So what is D? Okay, so if you go back here, D, okay, D is the degree, the angle for each reading that I'm going to get. So this angle D here, so within that angle D, okay, I want to be able to get the points and get the best fit line, correct? So of course the parameter D controls the likelihood, because if my D is too big, then I'm going to have a lot of points and I'm trying to get a single line within a very wide angle, which is going to be difficult, correct? But if my D is small, my angle is small, then the points that I get, I can sort of fit into a line within that small angle. Okay, so if I have more points that fall within the consensus, then I can more or less say with confidence that there is actually a landmark or a wall along this angle here. Okay, so that also plays a part. Okay, so these three statements all are true, okay, with respect to how the ransack algorithm actually works. Okay, so that is basically the end of the questions that I wanted to go through with you all. Okay, let me just quickly I stop sharing this first. Okay, so let me open up the document for the tomorrow's quiz instructions. Okay, so okay, so this is the instructions that is given to you all for tomorrow. Okay, so I think all of you have access to this. Okay, so you have 11 MCQs lasting 40 minutes. Each MCQ is worth 2 marks. Okay, again, we ask you to keep yourself free. Even though we are starting early, you just keep yourself free in case of any delays that we may experience. Okay, so just make sure you have the morning free, okay, just to focus on this. Okay, at 9 o'clock, okay, you are all supposed to report to Zoom. Okay, and we will be releasing the gradebook items, okay, for the Zoom as well as the paper links. Okay, we will assign you to breakout rooms as you come in. Anyway, for this one, there is no action needed by you all. We will be managing it. All right. Okay, so please, once you enter in the breakout room, make sure your TAs will already be there. So you need to make sure your camera is set up correctly. All right, and the TA also needs to mark your attendance. Okay, students are to log in, okay, solely on their mobile phone and must not log in to more than one device. Okay, so again, this is very important. So for the Zoom part, make sure you are logging into your mobile phone, okay, for the TAs to monitor your phone angle, okay, with your screen and your activities. Students are expected to comply with TA's instructions. Okay, so if the TA gives you any instructions that, for example, your camera needs to be tilted, or your screen needs to tilt a bit or anything, please comply, okay, and follow the TA's instructions. All right, and make sure that you're already in the breakout room. At 9:20, the Zoom meetings will be locked. Okay, so you have to make sure you're already in and you're already in your breakout room. All right, because we will lock the meeting after that, so nobody can come in. Okay, so nobody will be able to come in after 9:20. So you have to make sure that everybody is there and ready to be in. Okay, at 9:30 sharp, we will release the password. Okay, for the quiz, and it will start. Okay, there is also a link. Okay, so at the start of the or the front page of your quiz, we have already given you links. Okay, so actually in the practice quiz, I'm not sure if some of you noticed or missed it. Okay, if you look at the instruction to the students, there is actually a link for you to submit clarification questions. All right, so if you have anything that you want to clarify, you have to do it in those links there. Okay, so those links will bring you to a place where you can submit your clarification questions. Okay, and also a link for announcements. Okay, and of course the submission email address. All right, so if you remember, we said that it's compulsory for everybody to note down your answers in your Excel sheet and also submit them to the specified email address, okay, depending on which group you are assigned to. Okay, again, toilet breaks are not allowed, so please make sure that you so it's 40 minutes, so I think should be fine. Okay, you can only submit your Luminous quiz once. So this is very important. Okay, you are not allowed multiple submissions. So make sure that you check through everything. Okay, you're very clear, and then you submit. Okay, and again, 10:15 is the closing time for email submission. So 40 minutes is the quiz. Okay, so 10:10, 9:30 we will start. 10:10 it will end. All right, and you are given another 5 minutes for you to email the submission of your Excel sheet to the specified email address in your question paper. All right. Okay. If you have any issue suddenly tomorrow morning, okay, I mean, hopefully nothing goes wrong. But if suddenly something happens and you are unable for some reason to take the quiz or cannot, go into Zoom, something happens, quickly contact by emailing all 4 of us. Okay, all 4 of us email us. Okay, so that at least one of us who happens to see can quickly try to address the matter and try to see what we can do for you. Okay, make sure you have Zoom installed. Okay, and only Zoom on your handphone must be running. You must not run Zoom on your laptop or desktop. Okay, so all this, I think most of you already done with or have some experience based on the sample quiz that we did the other day. All right, again, all these are standard instructions. Your handphone should be plugged into power to make sure it suddenly doesn't die off. Okay, and your handphone's speaker volume is also should be high, so that if the TA needs to send any instructions to you, okay, you are able to hear it. Okay, and everything should be reachable. Okay, once the quiz starts, you should not get up from your seat for any reason. You should have everything on standby at your desk. Okay, so whatever you need to adjust, your aircon, your fan, your lighting, everything, okay, please make sure you have it. Your writing paper, pen and pencil, everything, make sure you have it. Okay, of course you can have your soft copy of your answer sheets that you your cheat sheets, okay, for you to have reference to. Okay, again, your Excel sheet is for contingency submission, but it is to be made regardless of whether Luminous fails. This is important. Okay, you must make sure you email us the Excel sheet even if everything goes well for Luminous. Okay, all right, so that is again a backup for us, so that you yourself have a copy and we have a copy of the answers that you had submitted. Okay, if something happens to Luminous. Okay, all right, so all this assessment procedure, again, I think you can, it's very similar to what you did the other day. Okay, the gradebook items, inside there you will have your quiz packet zip file where you have your Zoom link and your zip file link. Okay, so this procedure is again what you need to do for tomorrow. Again, while you are answering them on the luminous, also try to make sure you mark your answers on the PDF, and if not, also please update your Excel sheet at the same time. Okay, don't wait for the last minute to update your Excel sheet. While you're answering them in the luminous quiz, also update them in your Excel sheet so that the moment the quiz ends, you can submit the Excel sheet at the same time. All right. Okay, you must submit your submission on luminous. Okay, so you cannot complete all the questions and just not click submit. Okay, you have to make sure you click on the submit button, then we are sure that luminous has captured it. All right. Okay, and once everything is done, the time is up, and you submit. Wait for the instructions from your TA. Okay, before the you decide to log off. Okay, so until then, please wait. Okay, let me see this. Okay. Okay. Any questions you all have about tomorrow's quiz operation? So it's very similar to what you did the other day. So I think you have some experience in it, so which is good. Any doubts that you have, any clarifications that you need regarding the procedure for the quiz? Okay, so if no questions, what I would like to just preempt you is the quiz is tough. Okay, it is definitely tough. Okay, um, so that's why it's only 10 questions. All right, I mean 11 questions, but uh, if you know your material, you should be able to do them. Okay, and I say it's tough in a sense that not that we are going to suddenly throw you something you've never seen before. Whatever that is going to be asked is definitely things we have covered. It is tough in a sense that it takes time for you to uh, understand and the whole scenario of what is happening, and then you can answer. Okay, so it's not so straightforward. The questions are not so straightforward that the moment you see you can immediately know the answer. No. Okay, you will need to understand the question, work out some things, okay, and then only you'll be able to derive the answer. Okay, so all the questions are like that. Okay, so there's no single question where it's a giveaway. Okay, all the questions you have to spend time to look at it and absorb it, and then only you'll be able to answer. Okay, so you have to make sure that you are ready for that. So there are no giveaway questions, there are no freebies or anything. Okay, every question has a significant amount of work, a significant amount of thinking to be done. Okay, so in that essence, I'm saying it is a bit tough. Okay, but as long as you know your stuff, you'll be keeping up with whatever that we have covered in class, then I think you don't have anything to be particularly worried about. Okay, so anybody has anything else you want to ask? Okay, if not, I don't want to hold you back because I know you all are having a lot of things that are due this week and next week and so on. Okay, so okay, so is it open book? Okay, in a sense, you can. What I would suggest is you try to put all your material in multiple sheets of paper, either soft copy or hard copy, to make it easier for you to refer to. You can try to compress your information into a few soft copy slides, okay, so that it's easier for you to refer. Trust me, if you're going to go through your lecture material at that time to try to figure out something, you won't be able to do it. Okay, so that is why I say it's much more better if you are able to sort of compress your information into the a few cheat sheets, okay, soft copy or hard copy, so that it's easy for you to quickly refer and get on with the question. Okay, you really do not have time to flip through your lecture material at that point of time. Okay. Okay, so that's about it for what I had to cover. So I will not hold you back. Those who still have any questions, you can stay on and you can ask me in the chat. Okay. If not, those who want to log off can log off. Okay, and all the best for tomorrow's quiz. Okay, thank you. Okay, so I will stay on. Okay, for anybody who has questions. So so you can put in the chat. Okay. Okay, so for the submission, you do not need to submit the PDF file. But if you want to submit together with the Excel file, no problem. Okay. Like I said, whatever you email to us within the 5-minute deadline is for us to keep as a reference of your submissions. Okay, so it can be your Excel file together with the PDF file or just the Excel file. All right. But we will take the Excel file as your submission in the event that the Luminous fails. Okay. So the Excel file is the only thing that we will take as your submission. All right. In case Luminous fails. So make sure the Excel file is submitted to us. Okay, so let me answer some questions. So the private public key thing, if you use public key encrypt, can you use encrypt? Okay, so the whole idea is the public key should not be used to be able to decrypt because the public key is meant for everybody to have access to, correct? So you only want to be able to decrypt using the private key. Okay, if you can use the same public key to decrypt, then there is no point in encrypting and decrypting anymore. Okay, so definitely the encryption you can do with public key, but the decryption is private key. Yes, you can use calculators, no problem. Okay, but of course use your proper calculators because your handphones would be used for the Zoom. Okay, so make sure you are using a separate calculator. Okay, so if we need to ask you to refer to any registers and so on, okay, we will definitely give you that information. Okay, you're not expected to memorize any of those bits in the registers and so on. Okay, so we will, if there is any configuration of registers, that register bits and so on will be given in the question. Yeah, so the question about the CA public key, yes, the CA public key is inside the certificate, okay, of the CA. Okay, so that's about it. Okay, if you have anything else, I think most of you have my number. Okay, I'll just put it here anyway. So if you have anything, you can always message me. Okay, and clarify. Okay, if not, have a good rest and good luck for tomorrow's assessment. Okay, so thank you everybody. Okay, have a good rest. Don't panic, don't worry. All right, just uh, relax, and I think you all will be good. Don't not to worry. Okay, thanks everyone. I'm going to end the meeting now. Again, if anything, you can always privately email me or message me. Okay, I will reply to you. Okay, thank you. Bye.